Uh, so let me also thank the organizer for giving me this opportunity to talk here. So I will be also talking about many body localization. So already we have heard a few talks on many body localization. So mainly I will be talking about dynamical properties and mostly about numerical experiments on usual many body systems. I will show you what we think is going on from the perspective of dynamics. So whatever I'm going to talk about is mostly on these three work. Okay, so the setting, I want to start with the following idea that I still have a 1D system, so I will be concentrating in 1D system, a 1D system with many particles, and it's experiencing random potentials as the usual. And if I do not have any interaction, as we know that each of these particle will be localized, so this is Anderson localization, and this is kind of already very well known and well studied. So this is the setting, and the question that I'm going to ask, or the question of many body localization, is whether this thing is stable, or this localization is stable in the presence of interaction. Good. So why at all this we ask that whether there is a stability or not? Because let me tell you what happens in the presence of interaction given this system. Yeah? I'm going to show you this thing. So what has been plotted over here is what is called return probability. So you can think about it that there is a 1D chain, and I put some density somewhere in the middle of the chain. And I ask under the time evolution, what is the probability of finding that density again? So if it is 1, so then the particle never moves out. If it is going to 0, it goes to 0. Good. So this is what is written probability. This is just one sample, one disorder configuration, and what is plotted here is a function of time. Now the solid line, what you see here is essentially what happens in the absence of any interaction. Right? So what happens is essentially this highly oscillating return probability behavior, and that one can understand very easily. Yeah. So this is essentially the particle is localized within the localization volume. So it's essentially doing some kind of an oscillation back and forth within the localization volume. And that's essentially the mesoscopic fluctuations that we have in a non-interacting system. So one sample, no averaging, nothing. Now you put a little bit of interaction. So there are two type of disorder I put. This is 1.5. I will come and comment on what this W is when we talk about the model in particular. But right now, what you can think about that this is a weak disorder, this is a large disorder compared to the hopping. Good. So these solid lines were the mesoscopic fluctuations were, and these were the fluctuations that was coming from the non-interacting system. But now you put a little bit of interaction, which is 2, which is of the order of hopping. And what you see immediately that these dot lines, and these dot lines is where the oscillations dies out. So in other way of saying that in the presence of interaction, we have dephasing mechanism. And this dephasing essentially gives even within a single sample, all oscillations dies out because of this destruction of quantum coherence. So that's the naive picture, or not the naive picture, this is the picture. And then one can ask, even given all of these things, how can MBL or the localization phenomena is stable? Because what one would expect that due to loss of coherence, everything will decay down. So the return probability will go to 0 eventually at long. So, but then again, as we know by now that the MBL is a stable phenomena, we do have localization, and that has many different signatures. Okay, so let me just go through some of it. Some of it has already been flashed here. But one of the phenomena that we see is a dephasing that gives rise to propagation of entanglement entropy as a log. So this is one of the early paper by Barderson, Polman, and Moore, when what they plot here is an entanglement entropy starting from a product state. So initial the entanglement is 0. So it's a bipartite entanglement entropy as a function of time, where J-perp is essentially the hopping amplitude, if you wish. If you do not have any interaction, which is given by this Jz, so if you have no interaction, so it will grow and then it will stop. So there is no growth of entanglement without any interaction. That's the localization physics, if you wish. So the particles is localized within the box of the localization volume. But then you turn on a little bit of interaction, which is 0.01, 10 times smaller than the hopping, and what you start to see that eventually at some point of time it follows the localization, means the non-interacting curve, but then it starts to grow up. These are averaged plots, so averaged over many disorder realizations starting from a nil state, so that's the initial condition. And eventually for many interaction, what they can show that more or less I have a collapse of this curve, and the x-axis is rescaled by the interaction. So the time scale at which it starts to deviate from the non-interacting curve is essentially proportional to the interaction state. That's for the weak interaction. So this is just the weak interaction. Good. So that's kind of one thing that happened in the MBL phase. So one should be a bit cautious here that in a sense that just by seeing that we cannot say that this is a MBL phase. So this can happen in many other situations. So this is just a other way of saying that this is just a manifestation of MBL, not a proof of MBL. Good. So that's another thing that at very, very long time, what you see is that when it saturates after a very, very long time, it has a volume law entanglement. So the steady state has a volume law entanglement in the MBL phase. Whereas in the localized phase, it will be just a flat line. Okay, so that's another signature of the fact that there is a dephasing mechanism that is in play, the information propagation happens. Good. So that's kind of an old work, but recently now one can understand it in a more fancy terms in terms of OTOC. So this out of order time correlator, which is a 4-point correlator, we just heard about it. So this is essentially one example where you see that this is an ergodic phase, this is an MBL phase. So in the localized phase, so this is a contour plot of a sigma z correlator square as a function of time and as a function of space. And if the system is ergodic, completely ergodic, we see a ballistic propagation of information. So this is the light cone behavior. Whereas in the localized phase, what you see is essentially a bending of those curves, and it is logarithmic in time. Okay, so this is again the similar feature that we see in the entanglement entropy comes over also in the OTO. Good. So that's kind of my very short introduction to MBL, and what we know by now is more or less this type of a picture. It's kind of numerical picture, if you wish. Also, some initial work. So, for instance, this is energy density plotted as a function of disorder. So, I'm just giving a qualitative picture. So, I'm not putting any number anywhere. What we know that there is a mobility edge. By mobility edge, I mean that as a function of energy density or this is a closed system we are talking about, so it's a finite temperature in terms of temperature. At finite temperature, there is a phase transition, and the phase transition happens from an ergodic phase to an insulating phase in the presence of many body interaction. And the most important signature that one should think about is transport. So there will be no transport as an insulator. So that's kind of the important signature that one should look for. But as usual, so in numerics, this is very difficult to probe. So, but there are other consequences of these things. So for instance, this volume law entanglement in an eigenstate. So it's an eigenstate phase transition as well. So ETH holds here, ETH doesn't hold here. So there is an area law entanglement, so thermalization, so ETH, no ETH. And on top of that, there is also Wigner-Dyson level statistics that one sees in the energy level statistics and Poisson level statistics over here. So in terms of level statistics, also there is a transition that one can observe. Good. So this is more or less what we kind of believe in the MBL field, that there is this phase transition, and one can kind of in any generic 1D system one can see those kind of things given usual numerical caveats. Okay, so let me concentrate now on a given system, and I will tell you what are the observables that I will be looking. So I will be concentrating on this essentially the spinless Hubbard model, or in the presence of random potential. So epsilon I is a random potential. So nearest neighbor interaction, density interaction. We're concentrating at half filling. So half the total particle number is conserved. Then if epsilon I are chosen between minus W to W, V is 1, then it is believed that WC is close to 3.5. But later at the end of the talk, you will see that this 3.5 may not be so accurate. Good. So in order to contrast whatever I'm going to do, I will also put, instead of random potential, sometimes Aubrey potential. So this is not quite random. So it's a kind of a potential which is a cosine potential, but with a irrational number. So it's quasi-periodic. And I will contrast these two because there are certain physics that you will see that sometimes it exists in the random case and not in the Aubrey, and so on and so forth. Good. Yes, so it's a box distributed. Good. So the observable that I will be interested in is an infinite temperature correlator, two-time correlator. It's a density correlation function, and this n is essentially a normalization constant. I will be first of all be mostly interested in looking at the full profile of these things. This is important because the density is essentially related to currents, and the current correlator tells me about the transport. I'll be interested mostly about the transport of charge. Good. At the same time, I'll be also looking at the second moment of it because that gives me important information that if delta x is proportional to the t to the power half, so this half is important, and this half will tell me that this system is diffusive, and that one would naively expect again in an ergodic phase. Good. So this will be the most important thing that I will be after. But rather than just fitting and trying to find out the exponent itself, what I will be monitoring is the log derivative of this delta x with the log of t. The reason for doing so is that our system sizes and the time scales are tiny, essentially, because in a many-body system, I cannot go more than 10, 20, or that's the usual system size. And they are the things really quickly saturate, so the time scales are small. So what we will be looking at is this exponent, flowing exponent, and we will try to see how that thing approaches half or if not at all with respect to system size and times. That's the idea. Good. Let me first show the ergodic phase. So this is, before that, let me just comment on one small thing. So the clean system. So without the field, so previously I showed you that I will be looking mostly with respect to the field, but you can turn off the field. And already without that field, it's a XXZ model once you do the Wigner, and that thing gives you xxz, and at delta equal to 1, already the clean system has many interesting physics. So for instance, what we can show that the energy transport, instead of density, we look at energy correlator, will have ballistic propagation no matter what the delta is. So delta is the interaction strength, the V that I have shown it, written in the xxz language. Whereas if you look at spin or charge, delta exactly at 1, which is the SU2 symmetric point, one can show that this delta x square has a behavior which is neither diffusive nor ballistic. And right now, there are many activities that is going on, and many experts are over here. And what one sees here is that there is a KPZ type of scaling happening exactly at the SU2 symmetric point. And this is not only seen in the delta x square, one can do much more. One can show that eventually the full profile, so the full density profile or the spin SZ profile has a nice collapse if you do it carefully with the KPZ scaling. So that's just a side comment that indeed one can, the without disorder model is also very important and very interesting. So for instance, we learned about this GAZ-D, and this generalized hydrodynamics has been also applied in the delta 1 regime and so on. That's a separate story. Good. Let me put disorder into it now. So if I put disorder into it, what we see is the following thing. So this is an averaged correlator that I'm going to show you. This is this phi x is this density correlator for different disorder strength. That disorder strength I mentioned, that box distributed, and plotted as a function of x for this in a log scale, and for non-interacting system v equal to 0, when you have only disorder, we know systems is localized and has a correlation function which is exponentially decaying in. So that's the signature of localization. And that's what we see, no matter whether it's W1.5 or 3 and so on and so forth. So remember, 3.5 is an important number. We see that this is exponential decay. So this is a confirmation that my system is given the system sizes. So this is a system size up to 28. We have a localization. Now, what you see also that at a very long time, even in the ergodic phase, we do not see a profile which is a Gaussian type. Okay, so that's what one would have expected if I have a simple ergodic phase. So if you go to this system where you have a diffusion delta greater than 1 clean system, you will see that it is indeed nicely Gaussian. But that's not what you see. What you see here already is a very reminiscent of a localization physics. So it's a fact that there is a tent-like shape in a localized, in a log scale. It tells you that the diffusion happens in a very weird way. So, and that's precisely what happens. So there is no diffusion here. What we see here is subdiffusion. So this is precisely this beta of t. So this beta of t is this flowing exponent that I mentioned, plotted not as a function of time, but as a function of distance. So the reason for plotting it as a function of distance is that it's renormalized with respect to the non-interacting localization length. What I wanted to monitor is what happens to this beta of t when I exceed the non-interacting localization length, such that my interaction effects are enhanced. And what you can monitor clearly that going from 16 to 28, almost by a factor of 2, I do not see a convergence with respect to the exponent value itself. This is system size is too small. Will show that there are studies exist now shows convergence, but as of now, with this system size, you do not see any convergence, so there is no meaning of talking about exponent itself. But also at the same time, you see that it tries to grow as the time increase and as the system size increase. So one might naively expect that, okay, eventually it might go half, and whatever the subdiffusion that we talk about, which we talk about because we think that there is a Griffith physics, so rare region effects, which might not be true at the end. Good, but as of now, what I just want to point out that there is a flowing exponents which is not really well defined. That happens also in the W equals to 3. So here the flow is much less, but still there is a little bit. And if you monitor this curve, a little bit of upturns is also over there. What it suggests me is that this ergodic phase has its own, means the finite size effects in the ergodic phase is also very, very strong, even with the system size 20. Okay, so the reason for subdiffusion has been proposed is that there is a Griffith physics. The Griffith physics is simply saying that there are localized regime even within the ergodic phase that kind of slows the dynamics down. So there are region which is more disordered compared to the other region in the space. So the particle goes much slowly in this small region. Therefore, there is subdiffusion. Good. This thing can happen in the random disordered case, but cannot happen in the Aubrey-Andre. That's what I told, that it is a deterministic type of potential, and one would not expect to have a Griffith physics there. That is why I will compare it now with the Aubrey-Andre thing. So this is exactly the same thing, ergodic phase of the Aubrey-Andre model. When I say ergodic, I mean that at least one of the indicators shows that this is in the ergodic phase, either the level spacing statistics, the entanglement entropy, or one of it. Okay, so again transport, and what you see here as the time increase, so it's a weak disorder, it's an intermediate disorder. What you see is that this thing relaxes, not relaxes as it was previously, but it is relaxing. However, there are oscillations even after a very, very long time. And one can clearly see that these oscillations are coming from the potential itself. So whatever sigma or whatever the irrational number you put in, this oscillation is essentially going to match with that thing. In some sense, and this is true even for higher disorder. So here also there are these oscillations. This is averaged over many configurations, but still there are these oscillations. And these oscillations are coming from the fact that there is an underlying potential which is deterministic, not completely, at least for these small systems. Good. So this is this beta of t. Again, you see a similar feature as you see in the random case. So again, we do not see any saturation whatsoever here, and whether it's a 1.5 or 3, you do not see anything over there up to system size 24 or 20. So we thought at least at this stage that this may be a completely finite size effect, and the ergodic phase is probably both in the random case and in the Aubrey-Andre case is diffusive. But that's probably not true. But so that's what I wanted to show. So these are the recent developments which happens very soon. So this is essentially by Sasha, who is sitting here. So this is a system size much bigger than us, at least a factor of 10, using matrix product state under the TDVP formulation. And what they show, so the observable is a bit different. I'm talking about infinite temperature density correlation function. Here it's a quench experiment where you start with a nil state and you measure how the imbalance decay. And what you see here is kind of an exponent. So this beta is not exactly related to my beta. So there may be some little numerical differences, but at least this is much longer system size and much longer time scale. Okay, so the first thing that you want to notice is the following. So this is the beta has been plotted as a function of disorder strength. What you see, indeed, it doesn't go to half. So this is going from 16 to 100, and 16 lies over there. So there is indeed a flow. So if you do 16, 20, 24, you will see somewhere in between. So whatever the previously thought of WC will change by now, because there is a distinct flow, and seems like there is a around 100, the exponent seems to be converging, though much less than half. So it's still subdiffusion, but the exponent has changed drastically. Good. So here we expect this is the localized phase. Here it seems has a difficulty in convergence and so on and so forth. But what kind of shows that there is maybe a finite exponent even in the localized phase? I don't know. Maybe you can Sasha can comment later on this kind of thing. But seems there is something. Good. That's the random case. There is also recent work in the Aubrey-Andre case, and what it shows that again, if you take different type of irrational number, the time scale at which it become localized or become ergodic, or at which value of WC it happens, it completely depends on what phi you choose. And that's not what I tried to tell in my previous plot, that indeed the phi matters. Sorry, the irrational number matters. Whether you take golden ratio or something else, the physics at which time scale it will equilibrate or at which time scale it will become localization will also changes. This first one is not my data. It's Elmar and Sasha. However, this is the difference. It's TDVP. So it's not the usual TEBD formulation. Yeah, it's a call. Still okay. No, entanglement also grows subdiffusively, in a subdiffusive fashion here also. It's not ballistic. It's not. Okay, so that's one thing, but I want to flash this result also that happens almost very, very recently. So this is a thing that is again TBD. So this is some kind of a different thing. So it's a boundary driving, non-equilibrium steady state they reach. So this is a work by Skardikio and Nidarich, where they're trying to say they can measure the current itself very long time, and they can calculate what is the resistance. So from these calculations, so this is a TBD, much larger system size. And the reason for calculating resistance is the following. So if you have a Griffith physics, or there are portion in the system where the resistance is large, then if you know the distribution of the resistance, it will not be a self-averaging quantity. It will have a fat tail. So one would expect if Griffith physics is there, there will be a power law tail of this distribution. Good. So what they show, it's not yet published, but what they show very, very recently, that this is a very weak disorder where with increasing system size, first of all, this is in an exponential scale, in a log scale, so the tails are not power law at all, so these are exponential tails. Not only that, this is shrinking distribution, which implies that there is a self-averaging property. So now what it seems more and more that that the Griffith physics, there is maybe subdiffusion, but the origin for subdiffusion may be completely different than what initially has been thought. That's kind of the another thing that I wanted to. Good. So this is all about the ergodic phase. Let's go to the localized phase. So if I go to the localized phase and I look at the same thing, so I look at the second moment of the distribution. So this is large disorder 5, 6, 7. And what you see here, delta x as a function of time. So this is again compared with the random case, and this is an Obriander case. These flat lines are the non-interacting results. So that you see a little bit of noise in the data because it's not much averaged over. But what you see, a thing that there is a growth in the presence of interaction. The presence of interaction, even in the localized phase, this thing doesn't seem to saturate yet. Okay? So that's the exponent that I was also mentioning in the DEVD calculation. So this is again true for random as well as Obriander model. So there is nothing seems not so different in both the cases. But in the localized phase, what we see is a slow growth of the charge propagation as well. What does it mean? So there are many things that can happen. First of all, the first thing that can happen is the following, that the WC that we have thought about, which was 3.5 or so, it's much farther down in that range. It may be 6 or 7, or it can be even large. Okay, that's the number one thing. The second thing can also happen, that we have a finite system size. So even in this regime, we see there is a little bit of system size effect. Although one needs to understand that the growth is not that much. So the non-interacting localization length, so which can be approximated from delta x, is around 1. So the non-interacting localization length is around 1, the system size is around 30, but still we see in the presence of interaction there is a little bit of a growth. So that's important. So even there, some kind of finite size effects are there. So we are probably still in the critical regime. So if you draw kind of a quantum critical diagram, then there is a 1 over L correction, and we are in that regime. Therefore, we are probably seeing those type of effect of the critical physics. Although also we know that there are certain RG calculation where it tells that the critical point may be localized critical point. So that's kind of a riddle, I would say. Good. So let me just show you one experiment at least, which is the first experiment which calculates the transport. Until now, everybody was calculating imbalance. So this is the first experiment by Markus Greiner, which just published, which measures the transport distance, or essentially a 2-point correlator, the first time. And what you see here, this is as a function of time. This is a cold atom experiment, and what you see that for the thermal case, or for very weak disorder, is very quickly saturates. So the system size is with 50 atoms. And then at the critical, or what they call critical, which is 4.8 times J, there is a growth, but also what they call MBL, there is a growth. So this is kind of the confirmation, and this is what one should look at. So this is an exponent as a function of disorder strength. What you see, even at W8 or even 9, the exponent doesn't go to 0. It's still fine. This is, I think, it's still an open thing, and whether this will ever be, it can be a log also, as usual, and whether there is a thermalization even at a very longer time, this MBL phase is not so clear, at least not with this kind of experiments and the numerical experiment that we have. Good. So at this point, let me conclude what I have talked about, and then I will talk about something else. So I've talked about slow dynamics in the ergodic phase, but I think that the rare region effects are much less than initially thought about. So second thing that I also mentioned, that the quasi-periodic potential also has a slow dynamics, but seems there the effect is more finite size than anything else. Third is that the critical disorder strength is much larger than initially it has been thought about or predicted, which was around 3.5. And fourth, I want to also mention that there is residual dynamics in both the random and quasi-periodic potential in the MBL phase, which is kind of I would say not expected. Good. So let me try to talk about another different type of MBL phase. I have some more time. 10 minutes. In 10 minutes, I will talk about a different MBL phase. So I'd like to talk about now what happens. So until now, whatever I was talking about, there was no symmetry we mentioned. Now I want to talk about what happens if I now have a symmetry in the problem, some sort of a symmetry, and what happens to that MBL phase, whether there is at all an MBL phase or not. Okay, so to start with, there are some work already. So for instance, if you start with a SU2 symmetric model, so this is a Hubbard model, the spinful Hubbard model, where this T sigma is essentially controlling the SU2 symmetry. You have a Hubbard U, and what has been now understood that this SU2 symmetric Hubbard model might not have any MBL phase at all. How so? So here we already know that there is a charge which is localized, but one can show, so this is a spin correlation function as a function of time, and what you see that if t equals to 1, which is the SU2 symmetric point, and this is the way of going away from the SU2 symmetric point, that if you are at the SU2 symmetric point, there is the spin that has a sub-diffusive dynamic. And as you go away from the SU2 symmetric point, you start to see more and more flattening of this data, which implies that there is a localization. Good. So similar thing happens. So there is a series of work by Protopopov and Abanin, where they show that the eigenstate of this SU2 symmetric model has not an area law entanglement, but a logarithmic log of L entanglement group. So what does it mean? So the idea is simple, that there is a charge which is localized. So you would expect that there is an MBL in the charge sector, but the spin is still sub-diffusive. So the spin acts as a bath to the charge. So eventually, at a very, very long time, the charge will also eventually delocalize. That's kind of the idea, and that's why also there is this log, and that's the idea of this type of symmetry. What I would like to talk about is slightly different. Is what happens in the presence of particle-hole symmetry. This is a situation where you can think about there is a bond which is this. So this is the non-interacting model of such a thing. This is a very well-studied model. So starting from 53 and so on and so forth. This is called Dyson singularity. What happens in the non-interacting case already is that the E equal to 0 state or close to E equal to 0, the density of state diverges. Non-interacting, nothing about interaction. The divergence is what is known as Dyson singularity. Not only that, not all the states in this system is localized. Even though the disorder is as strong as you want, what happens is that the localization length has certain fluctuations, and the states are quasi-localized, which is very different than what you have for the random case, where in the random case you have all states which are exponential. Here it is not the case. There are fluctuation which grows with the system. Good. So a little bit of work has been done. So for instance, one of the RG work, one of the early excited state RG work shows that in this type of system, you will have an entanglement propagation, which is called quantum critical class. So this is a critical system in some sense with a log propagation. So there is no interaction, no dephasing whatsoever, but still you have a propagation of entanglement, which is super double log. Good. It's a real space RG. It's a version of real space RG in the okay. So what I would like to understand is what happens in the presence of interaction that preserve particle-hole symmetry. So what is the role of the zero energy state if you have interaction and so on and so forth? Good. So let me show you the result, and then I will hand-wavingly argue what do we think about it. First of all, if you look at the usual thing, so level spacing statistics, if you look at the level spacing statistics as a function of disorder, you would definitely notice that there is a phase of this in this model which is ergodic, and then you flow down to the Poisson statistic. But with this usual thing, so usual thing is the fact that with increasing system size, there is a crossing which shifts. Okay, and where it stops, we don't know yet. So that's one thing. And this feature I would like to also mention that appears also in the random case, also appears in the random regular graph, and so on and so forth. So this is kind of a very tricky situation. Good. But you also see that the entanglement, eigenstate entanglement has a page value, which is the ergodic value or the thermal value, but eventually it goes down. But even at very large disorder, also there is a correction. It's not completely. So if you plot this kind of thing, so S, which is this quantity, the entanglement entropy, bipartite entanglement entropy divided by the page value, which is the thermal value that you expect. What you see is very interesting thing that for smaller system size, initially it tries to go down. Going down implies localization, but at some point of time it realizes that it's not supposed to be localized, so it turns back. There is kind of a correlation volume kind of thing. Until and unless you reach this correlation volume, it will feel that it is localized, but eventually it will become. And this kind of keeps on happening. We have not much system size, so we cannot do any scaling or so in case, but at least this is an indicator. Good. The second thing that I want to show that the entanglement growth. So entanglement growth deep in the MBL phase. Again, when I say MBL phase, I mean that there is a Poisson level statistics, or at least naively Poisson level statistics. But you see that the entanglement growth is not log but power law. Okay, so that's the first thing. So this is a log-log plot for different system sizes, and there is a power which is around 0.3 or something accurate. Not only that, the growth of this thing is not any more volume as one would expect in the case of random case. Here, what we see is a log growth also. That happens in two different disorder strength, 2.25 and 2.75, but also this power law changes. So anyway, so the small time scale, small system size, one cannot really trust all these numbers. So moreover, not only entanglement, let's talk about this the charge propagation. So this is the charge propagation. So this is delta x. What you see here, even in this localized phase, which is this strong disorder. By the way, this disorder looks small, but this is exponential of the thing, quite large. So this thing grows. So this is we cannot do to much longer time. So this is the time of 10 to the power 10. But within the time scale that we have, what we see is that always so this is a very different situation. So this is again a return probability, which one would expect that it saturates, but again one goes to longer and longer time scales, and what one sees that eventually it shows some kind of a pre-thermal kind of a plateauing. So which is what we would expect for a localized phase, but eventually it goes down once the time scales is in. Now what I would like to understand, or at least hand-wavingly, why this MBL phase, which one would expect to have MBL, it's not really an MBL phase. There is some kind of a hopping process that gives rise to whether it's a charge transport or an entanglement transport. Good. So for that, let me just go through this little exercise. So this is our original Hamiltonian. So I wrote those Hamiltonian in the Anderson basis. So if you wish, the disorder is over there. This is the diagonal part. And then there are interaction, which looks like that. So these are the interaction matrix element that is essentially given by the non-interacting wave function. Good. So particle Hall symmetry implies something special about this Hamiltonian. The first thing that it implies that there are the energy comes in pairs. So the positive energy and negative energies, there are always two energies that is come. That's the first thing. The second thing is also that the wave functions are related by each other. Other way of saying that these two energies have wave functions which has same localization center. Okay? And that's interesting. What it does is the following thing. It's a very simple idea that these wave functions, if you construct states with this property, then you will see the following thing. So by this property, I mean that let's construct a state which looks like that. So in this F basis, which is the Anderson basis, we construct state with minus k and plus k. So this has energy which is this plus this, which is 0. So this is a 0 energy states, but two particle states. I'm constructing two particle bound states. So essentially, I'm projecting the full Hamiltonian in the two particle space. In that space, if I create those bound state, they are going to stay together, because this is essentially in the real space have a localization center which is same. So therefore, it's essentially creating particles at the same point or one lattice size distance. And if you do that and you do a simple perturbation theory, you can write this Hamiltonian in this two particle subspace as the following Hamiltonian. So the energy is 0, so there is no term, no kinetic, this kind of diagonal term. But then there is an effective interaction term which looks like f dagger f, f dagger f, but with two different p's, and these p's are essentially these numbers. So what is happening, and this is, by the way, it's a first order approximation, so there are higher order terms. I'm just throwing away all the other order terms. So what is happening is the following. So if I create particles which are bound states nearby, two particle bound states in this Dyson singular system, then they will hop. Although all the eigenstates are localized, but they will hop and they will not go away from each other. And in this way, there will be some transfer. And indeed, that one can see. For instance, this is a calculation in this subspace, in this two particle subspace. So this is essentially the sigma plus, and the sigma minus is the center of mass coordinate and the difference of mass. And what you see with increasing in this disorder strength, the center of mass moves, which is this bound bound state propagation, whereas they don't leave each other. Good, so let me just finish it. My time is over. Let me thank Ferdinand and Felix for the first part of the work, and Giuseppe and Marcus from Dresden for the second part of the work. So these are the funding agency. So this is what I have been talking about. So I talked a little bit, mentioned about the KPZ scaling at the SU2 symmetric point. I talked about that there is a flow of exponent in the ergodic phase, which kind of true in the both in the random and in the Aubrey-Under case. I also talked about a little bit about the localized phase itself shows very interesting dynamics, or maybe sub-phases, fractality, many things. And also I also want to mention that in the case of particle-hole symmetry, it seems, even though naively one would expect an MBL phase, but we see that there is a possibility to have no MBL phase or anomalous thermalization as like SU2 symmetry. With this, I would like to thank you.